12.3 dot product part 2. We have a theorem, u dot v is equal to magnitude u magnitude of v cosine theta, where theta is the angle between vectors u and v. And this is actually a physics definition. Physics, they define the dot product this way, and they use the math definition as a theorem. Which way you do it is really just a matter of choice. Just as a simple illustration, let's suppose we have two vectors here. V, which follows the x-axis, and u, which is at a 45-degree angle with the x-axis. And the magnitudes are 10 and 15 respectively. We can write u in component form, we saw this last section, as 10 cosine 45i plus 10 sine 45j. Those are just really adjacent and opposite sides of a triangle, a right triangle we can construct. And v is just 15i. I says delta x equals 1, and 15 times delta x equals 1 is delta x equals 15. Very simple. Now, if we use the component definition of the dot product, I've replaced cosine and sine 45 with square root of 2 over 2, square root of 2 over 2. I guess I could have simplified this. It would have made it a little easier. When we dot this on 15i, it's this times 15 plus this times 0. And you can, 10 over 2 is 5. 5 times 15 is 75 radical 2. Now, if you use the physics definition, that's just simply magnitude u, which is 10, magnitude v, which is 15, cosine 45. Cosine 45, square root of 2 over 2. 10 times 15, 150. Over 2 divides into 150 75 times. Same answer. You always get the same answer. This actually has a physical definition. You can define something called work if one of these vectors is force and the other one is displacement. And then the dot product ends up giving you work. Whereas the math definition we talked about is easier from an axiomatic standpoint. Very easy to use the math definition to prove the physics definition using the law of cosines. We're not going to go into that. You could, if you're interested in that, just go ahead and Google proof of dot product theorem or something like that. I'm sure it's available. If you want me to prove it in a Zoom session, feel free, challenge me, and I'll show you a proof of it. It's not that complicated, but we got other things to attend to. Now, this theorem is fairly useful geometrically. You can solve for cosine, and we have cosine theta equals u dot v over magnitude u magnitude v. Gives us a way to find the angle between two vectors. And almost seems like circular reasoning, but what we do is use the math component definition here. This allows us to find the angle between two vectors. Now, let me give you a very simple example. Let's take 3 points in, we can do this two-dimensionally. And let's suppose this is the point 5, 5, and this is the point 4, 1. And let's suppose this is the point 2, 3. And we construct a triangle, and we want to know that angle. Very easy to find the lengths of these three sides. This side is, let's see, 5 minus 2, that's 9, and 4 is square root of 13. This side is like 1 and 4, that's square root of 17. You can use a distance formula. This side is 4, and 4 is square root of 8, 2 radical 2. And given three sides of a triangle, how do you find an angle? Well, it's very simple. You use the law of cosines. That's a standard 11th grade math problem. What we're going to do is just construct a couple vectors and find the angle between two vectors. It's actually much simpler. And we'll call this vector u, call this vector v. And u That's just simply we go from 2 to 5, so we get 3i. And we go from 3 to 5, and so we get 2i. Let's find v. We go from 2 to 4, so we get 2i. And we go from 3 down to -1, -2j. There's our two vectors. Now we want to find cosine theta. And we want u dot v. Okay, u dot v is 3 times 2 plus 2 times -2 over magnitude of u, and that's the square root of the sum of the squares. 3 squared and 2 squared is 13. That's this right here. So we have square root of 13. And magnitude of v, we already know that's square root of 2, but you can square 2, square -2, add them up, square root of 8, 2 radical 2. So we get times 2 radical 2. You could use square root of 8 if it's easier. And this simplifies to 6 minus 4 is 2 over 2 square root of 26. You could even simplify that to 1 over square root of 26. A fairly easy process. Well, in any event, we end up with theta is inverse cosine 1 over square root of 26. Okay, and that's an easy peasy calculator step. I'll leave that to you. And of course, now we don't have to use law of cosines, and naturally, we proved this definition using the law of cosines. So somewhere along the line, you have to use law of cosines. You can't get by that. It's part of the mathematical structure, the geometry of what's going on here. So very useful formula. You'll see that in the homework as well. So that's the end of part 2. We'll be back with vector projections shortly.